Hi, everybody. So I also want to thank Zurich Instruments to reach out to me to ask me to give a talk about my PhD thesis. And I'll be talking about the PhD results in Christian Schullenberger's group, who is also present today in the audience. Let me go there. So I'm breaking my talk into three different parts. It was actually good that David does talk about the Andreev physics, so I can probably keep my my first part short. Since Andreev qubits is a rather new concept, I want to introduce the physics of Andreev bounces to you to give you a bit more of intuitions about Andreev bounces. Then I will come to talking about my research, and I'm going to conclude in my third part. Right. So, and I want to first start with something which physicists know. So let's say if you take a piece of normal metal and you interface this with a insulator, and you have 3 electrons in normal metal. The electrons, they will be bounced back at the insulator. Now, if you take 2 insulators, then you can actually confine electrons like between these 2 insulators. What happens if you remove the insulator with a piece of with a piece of superconductor? The following scenario can actually happen. Do I have the laser pointer? Yeah. The electron can still be bounced back at the interface to the superconductor, but instead of having a reflected electron, you can actually have a hole, and you create also a pair, a Cooper pair inside the superconductor. By doing so, you can confine electron and holes between 2 pieces of superconductors, and that is basically the idea of Andreev bounces. It's about confining electron and hole pairs between 2 superconducting electrodes. So in the reality, I work with nanowires. I will also talk about this a bit more. So you take a piece of normal metal in the middle, and then you put 2 superconducting electrodes around it. The superconducting weak link, that's a device which we call weak link, can have a superconducting phase difference, and the weak link itself also has a certain transparency. As David already has pointed out, the typical energy spectra of such a weak link looks like this. You have a lower state and also an excited state. Yeah, and since I want to give you a bit more of the intuition, I'm also plotting like what exactly happens inside this superconducting weak link when you are at different points on this energy spectrum. So if you look at the red circle here, you see that the current goes in the left direction. It forms a bound state, an anti-clockwise bound state. And if you look at the green circle, the current direction is opposite. And if you're exactly in the middle, then there's also no current because of the normal reflection, which can happen inside a superconducting weak link. The formula you have also seen, the current which is associated with the Andreev bound states goes with the slope of the energy ion states. Right. So, and then there's another effect, namely the spin degree of freedom in the system. That's something which we don't have in transmons. What I haven't told you so far is there was so far no mechanism to distinguish between the spin up and spin states of the Andreev bound states, right? So again, we're looking at the left spectra here, the left spectrum here. You have the typical short ballistic limits Andreev bound states. You can make the weak link longer to introduce more Andreev bound states. Each of them, they are spin degenerate because there's no mechanism to distinguish between spin up and spin down. As soon as you also introduce spin orbit coupling into your system, you can break the time reversal symmetry, and you also split then the Andreev bound states into like a doublet of a spin up and spin down states. This is interesting because then now the supercurrent is associated with also the spin of the Andreev bound states, and people actually found out that the energy relaxation time of the spin states can become longer. I think that also sort of like answer one of the questions before. Why do people look into bounded states into superconducting weakling? Because there's it can be that the energy relaxation time gets longer. Good. So since we are dealing with like quasi-particles excitation with the superconducting weak link, we can also define a parity in this superconducting weak link. The even parity, people usually describe this as the subspace where you have an even number of quasi-particle excitations. So the ground state there would be, the ground state of the weak link, and then the excited state would be the one with two-fold excitations. That gives you a computational subspace. You can define an Andreev level qubit in the even parity, or you can also utilize the spin degree of freedom to define a spin qubit in the odd parity. So this is the definition of the qubits. Now we have the qubits. How do we read out the states? Was also mentioned before by Davidas. Essentially, we know from previous slides that the underbound states, they carry supercurrent. So what we can do is that we can couple the superconducting weak link to a microwave cavity. Because the microwave cavity can give you the 0-point fluctuations, and that can couple to the supercurrent inside the weak link. So you can write down this Hamiltonian. In the first order, you have the coupling of the cavity, the 0-point fluctuations to the first derivative of the weak link Hamiltonian, which is essentially the current. So we know underbound states can couple to cavity, and immediately we also know that we can perform non-demolition measurements when you couple the cavity dispersively with the underbound states. We know that we can also use microwave excitations to drive dynamics of the weak link, and we also know that we can use a cavity to mediate long-range coupling of the Andreev qubits. So much about the background. So what have people achieved actually in recent years? It's a rather new concept. The whole business about Andreev qubits started in 2015 when a group in Paris, they actually managed to demonstrate for the first time the coherent manipulation of the pair transitions. So they did this at the beginning in the superconducting atomic point contacts. 3 years later, people realized this also in the indium arsenide nanowires. And then people found out, hey, we can also use a spin orbit coupling in indium arsenide to activate the spin degree of freedom. We have seen this image already before. You can actually trap a single spin inside the superconducting weak link and measure the coherence time of this spin state. So much about like single qubit realizations, since we have been doing so much in that field. Then we can move on to like thinking about coupling two of them. And that results into two very nice publications in recent years by a group from Delft and also by our group. So in these two manuscripts, researchers demonstrated like two different ways to couple two underbound states. So what I want to show on this slide is that to tell you that what kind of milestones Andreev qubits have achieved is still a very new field. We are only at this stage to, for the first time, realize the coupling of two of them. Right, now I'm coming to my research. So the goal of my research was, so when I started my PhD, I've already seen that, okay, the Andreev qubits, they are coherent. We can measure some sort of like time scales there. And now we need to come up with a scheme to couple two of them. And I would like to have a long-range coupling because that is also the design of the quantum chip. But how would this actually like coupler look like? So it should be a coupler which couples two Andreev qubits, and the behavior of this couple, this circuit, should be described by a Tarvis-Cummings model, because we know this model describes the coupling of two quantum systems with a cavity mode. So my goal was to go to lab to make such a circuit and measure this. Right. As material, we don't have heterostructures as David does. We use indium arsenide nanowire. They are not scalable, but for the research purpose, they are perfectly fine because they are clean. We don't have to deal with like lossy dielectric materials. It's a great material. Yeah. Here on the left, you see a TM image of such a nanowire. The dark gray region, the vertical one, it's the indium arsenide part, and everything around it is the epitaxial aluminum. So researchers from Copenhagen, they grow those nanowires in MBE machines, and then afterwards, they deposit aluminum from the side. As you can see from this SEM image. We in the lab, we make the chip, and then we make first a resonator chip, and then we suspend our nanowires on top of the resonator chip. And then we also etch away a small section of aluminum here to form the qubit. I want to emphasize again, the physical location of the qubit is really like within this small 200 nanometer segments of indium arsenide. It's very different than the transpons, which is like 100 micrometer big. Great. And then I also come directly to the coupler. This is an optical image of the coupler. Let me break it down. So the horizontal transmission line, which you see there, that's the cavity coupler. That's 6 millimeter long. At the ends of the cavity coupler, we place our indium arsenide nanowires. As I already said, they are like 200 nanometer big. And then we also defined gate lines and also flux bias lines there. A special thing with this coupler is that we also introduce an interdigitated capacitor at the center of the transmission line. For us, it was crucial to have this interdigitated capacitor because as we did our research, we found out that you can actually have current which pass through the center conductor from one ground to the other. And that actually kills the quality factor of the cavity we had. To prevent the current going through the center conductor, we put this capacitor here. And it actually brings you some very interesting features. Namely, by having this capacitor in the middle, we can form two different resonating modes with different symmetries. We have the symmetric mode here. At the frequency fs, when you look at the voltage amplitude, you see it's symmetric around the coupling capacitor. That's the dashed line here. And on top of that, or like below that, actually, you have the anti-symmetric mode, where when you look at the voltage amplitude, it's anti-symmetric around the coupling capacitance. Both modes have current antinodes at the ends to ensure that there's also coupling to the Andreev qubits, because we place our Andreev qubits there. The frequency of the anti-symmetric mode is a bit lower. One can analytically calculate this using the transmission line model. So about that. So first of all, in the first experiment, which we have to show is that indeed the cavity works as we want it to work. So we just took a very simple resonator spectroscopy measurement. We see that there's indeed resonating behavior at 6.46 gigahertz. And at around the anti-symmetric mode frequency, we don't see any resonating behavior, meaning that, okay, I've actually forgot one thing. So these two modes, let's go back. These two modes, they have two different symmetries. Now, the interesting thing is that by designing the microwave port, we can actually address one of the mode without addressing the other mode. In our case, we designed something which is known as a common mode, a common port, meaning that we have access to the symmetric mode because we commonly drive both half of the cavity. While we don't have access to the anti-symmetric mode because there you would need to have a differential drive, right? And to show that that's really the case, we took the resonator spectrum. We see that indeed we can drive the symmetric mode, and we cannot drive the anti-symmetric mode just due to symmetry reasons. Okay, yeah, and sorry. um, um, so since we have this difference between like driving one mode and not driving the other mode, we can do something which is pretty cool. We can use this mode to do the dispersive read of the qubits, and we can use the lower mode to couple the cavity, because we know that the lower mode also coupled to the qubit. It doesn't couple to outside to the external circuits. So there's no energy relaxation through the anti-symmetric mode to the outside. Okay, good. Then the cavity works. So we also have to first verify that the qubits are also there. So we took the qubit spectroscopy. We took the qubit spectra. I show you here the proximity, the optical image of the indium arsenide nanowires. There's a gate voltage with which we can tune the transparency, and there's also current to flux bias the loop. Here, the two spectra here, they show the two-tone spectra as a function of the gate voltage and also as a function of the bias current. And indeed, we see like, hey, there is an even parity transition, which can be tuned both by the gate voltage, again, by tuning the transparency. And we also see that this transition is also tuned by the flux. We did this for both the left and also the right qubits. So we confirm, okay, the qubit is there. Then we also did some time domain measurements to show that the qubits, they indeed have some coherence, so that we can like reuse them. Here in this plot, you see the typical Rabi Shefron pattern. What we do there is like it's a two-tone measurement. On the x-axis, we change the length of the drive pulse. On the y-axis, we change the power of the drive pulse. And we see that if you increase the power of the drive pulse, indeed the Rabi oscillation gets faster and faster. And you see that it gets like as fast as like around 5 nanoseconds. That's also another point which I will talk about at the end. From here, we can also extract the time scales of the qubits. The T2 Rabi is around 20 nanoseconds. It's not so great. We think that it's limited by the material, and energy relaxation that is around 1 microsecond. It's not a very good qubit, but as I already said, it's we're still at a very new beginning stage. But nevertheless, the coherence is there, so we also can perform the actual coupling experiments we want to do. Right. Good. So we show the coupler is there. The qubits are there, so we want to couple them. How do we do that? We first also have to verify that the qubits is coupled to the anti-symmetric mode. So we did also this experiment here. We detune the right qubit so that it doesn't affect our experiment. And then we tune the transition of the left qubit into resonance with the anti-symmetric mode. Indeed, we observe an avoided crossing there, which shows that, okay, the left qubit is coupled to the anti-symmetric mode. We do the same thing also for the right qubit. And we see like, okay, both qubits are now coupled to the anti-symmetric mode. So this is already a good starting point. On top of that, we also see this horizontal line here. And that's something which people who work on Andreev qubits already knew. Namely, because you have the parity switching between the odd and even states, for some certain time, the qubit can be in odd states, and that gives you the additional horizontal resonance here. Now that we know individually each qubit is coupled to a cavity, we want to bring them all on resonance. Oops. Yeah, okay, so from this measurement, you also extract the coupling rates and also the qubit decay rate. So we are confident that we can move on with our experiments. And this is one of the final slides I want to show. So in this experiment, what we did, we took the spectrum when we first hybridize the left qubit with the cavity mode, and then we sweep the right qubit across this hybrid system. we see a lot of lines here. We understand them. They appear because each qubit can be individually in the odd parity, and that gives you additional resonances. The most important resonance which we see here is one which is highlighted, outlined with the D, the say D here, and that's a state which occur if the whole circuit is hybridized, and that's something which is also predicted by the Travis-Cummings model. So that's good. We further confirm the hybridization of the whole circuit by detuning the left qubit and repeated the same experiment. So that gives a plot B and C here, and we see that the behavior is also well captured by the simulation with the Travis-Cummings model. So we know, hey, these two qubits, although they're 6 millimeters apart, they are still coupled. So the last slide, so that's the conclusion slide. Two take-home messages I want to give you about Andreev qubit is that first, the qubit is small, as you have already seen like multiple times now, and also the gate operations on the Andreev qubits can be very fast because there we are not limited by the unharmonicity of transpond. We realized, like for the first time, the long range coupling of the Andreev qubits. If you want to know more, there's a preprint on arXiv, and the work was not done only by myself, but also like by a lot of collaborators. With Christian's group and also other European universities. This is it, and I'm happy to take questions.